Lesson 4.9 is quadratic systems. The standard is something about solving systems of equations that involve linear and quadratic equations. Last chapter, I think it was last chapter, we solved systems of equations. So we've already solved systems of equations this year, but when we solved systems of equations, we didn't involve quadratics with it. We were solving systems of equations that were two lines, right? And so when we were graphing, we were looking at, okay, where do the two lines intersect? And then we also had our substitution methods and our elimination methods we used, right? Sound familiar, I hope? Okay. Today, the systems we're looking at, because we've just had a whole chapter over quadratic equations, involve a linear equation and a quadratic equation. Now, we're going to look just briefly at a couple of examples here. But what you have here on the top row are some pictures. And these pictures just kind of give you an idea of, okay, how many solutions could we have? If you have a quadratic equation, which what does a quadratic equation look like? It's a parabola, that U shape. Okay, so we have that U shape and a line. Well, a line is a line. How many ways can a parabola, a U, and a line cross? Well, for here, for instance, as we look at this one, it says there's two solutions. Do you see the two solutions? Because the line crosses through the parabola in two places. So your answer in that case would have two ordered pairs. Just like everything's been having two solutions this chapter, it would be two ordered pairs. Now, here's a special case where there is one solution. On occasion, you'll have a line only cross a parabola in one spot where it's what we call, do you guys remember our tangent? You remember that word from geometry? But like this line is tangent to the parabola. It just touches it at one spot. And then it is also possible to have no solutions. Normally when we say no solution, it's because the two lines are parallel. But in this case, it's the line goes outside of where the parabola is. Okay? Yes? Not in this lesson. It's not possible to have three solutions between a line and a parabola. Now, you get a different graph with more curves, then yes, we could have three solutions, but that's not something we're working with this year. Okay? Yes?
Did you say on the one solution, can it touch any point of the parabola, or does it have to be vertical?
No, you could have a one solution where the line is on the side at an angle. It wouldn't have to be the vertex. That is possible. Okay, so example 1 is solving using a graph. Solve the systems of equations by graphing, which means what we're going to do what? We're going to graph these two things, and then we're going to look for where they intersect, right? Okay, well, here's the toughie. How do we graph y equals x squared plus 6x plus 9? Not the quadratic formula. We want to graph this.
Eliminating. Substitute.
Okay, we can't eliminate or substitute to graph. What'd you say back there? Okay, if it was in that form, yes. Which actually, this one could be in that form because we could factor it. This one would factor actually into that similar form. Do you guys remember how to find the axis of symmetry? Guess what, guys? I said you're getting a review worksheet tomorrow. Guess what? This is all coming back, right? Okay. Negative b over 2a. If it's in standard form. Okay. Since this one is in standard form, we can think axis of symmetry. So think of this as, let's write the equation over here that we are working on. Think of this as 1x squared, right? So for your axis of symmetry, this is good review, x equals Negative b over 2a. What's negative b over 2a going to be?
-6 over
Okay. Negative 6 over 2 times 1, which is negative 6 over 2, which is negative 3. So our axis of symmetry is x equals negative 3. How do we find the vertex? Plug in that negative 3 into the equation there. So right now, I know my vertex is negative 3 comma something. I know the other number. I almost just wrote it in for you. Okay, what do I do with that negative 3? We put it in. And so, negative 3 squared plus 6 times negative 3 plus 9. Negative 3 squared is 9 minus 18 plus 9. What's 9 minus 18 plus 9? 0. So that tells me my vertex is negative 3, 0. That's coming back to you, right? Yes?
I don't know if I just point this to get it. Why is there an I before the x squared?
It's a 1. The invisible 1 I wrote in.
Okay, it's like a bunch of dots.
It's a 1. I was just kind of trying to get you guys to think, okay, that's a 1x squared, so a is 1. Okay. Officially also, do you guys remember where the y-intercept is? The C? Yeah. So this 9 right here is my y-intercept. Now, the fact that my a value is 1 can also help me graph this. Let's go ahead and graph this. Axis of symmetry, negative 3. Let me get this to where you guys can see. So 1, 2, 3. So officially, remember there are times you need to put that axis of symmetry in. My vertex is negative 3, 0, which is where? Right there on the x-axis, yes? Officially, we said the y-intercept was 9. Now, if my y-intercept is at 9, what does that tell you? Yeah, we're going to have to reflect across the axis of symmetry, which means, here's my axis of symmetry. This point that is at 9 is 3 to the right. So we also need an equivalent point that is 3 to the left. Now, based on the fact I'm looking for an intersection point, if I draw that, is that going to give me a very accurate parabola right now? Not really. Do you remember what your parabola looks like when the a value is 1? From if you think of the vertex as 0, 0, there's a set of points that are over 1, up 1, and there's a set of points that are over 2, up 4. You remember that XY chart I had you guys work with? 0, 0, 1, 1, 2, 4. So if this is my vertex here, I know there's a point that is over 1, up 1. Both directions. I also know that from the vertex, there are points that are over 2, up 4. Does that give me a pretty accurate parabola now? Yeah, it does give me a very accurate parabola. And the more accurate, the better. You say the more better.
Over 2, up 4 from the vertex. Okay.
from the vertex. If you think your vertex is kind of your 0, 0 point, over 1, up 1 from the vertex, and over 2, up 4. And notice the next set of points is over 3, up 9. We don't normally graph that set of points, but it happens in this one. Now, the other thing we need to graph, y equals x plus 3. Now you've got to dig even deeper back in your brains. How do we graph y equals x plus 3? Yeah, what form is this? This is, does that sound familiar? Y equals mx plus b? Dig deep, guys. It's in there. I know it is. I've taught it. You've learned it in Algebra 1. It's out there. Okay, so 3 is my y-intercept. And what else do you need to know coming out of this? Your slope is 1. What is 1 as a fraction? 1 over 1. And what's that phrase for that fraction? Rise over run. I do hope this one's coming back to you. I'll cut you a little more slack on the quadratics because that's newer. But y equals mx plus b, it's got to be there. So, y-intercept of 3. I'm going to go up 3. There's my y-intercept of 3. From there, I need my slope of rise 1, run 1. Up 1, over 1. Up 1, over 1. I'll be honest, going up 1, right 1 isn't taking me where I need to go. So what am I going to do? I'm going to reverse it. I'm going to rise -1, run left 1. Down 1, left 1. Down 1, left 1. Down 1, left 1. What happened as I was doing that? Did I touch my parabola? How many points did we touch the parabola in? 2. So was it helpful that we put those points there earlier? Very much so. That's unusual. I just freehanded that line. I never freehand lines.
Isn't it kind of like a lot of solutions or like points that essentially small? Can't you just say like equals a lot more than that?
No, it would just be these 2 places.
Well, if you got like closer.
No, officially it's just those 2 places.
So that it has to be like a whole number.
It wouldn't have to be a whole number, but it is in this case. The way these 2 are set up, they touch in just at the 2 points. Okay. Now, if the lines ran on top of each other or something, it'd be a different story. Then there's more than just the 1 or 2 points. But these just cross. Okay, folks. Don't move away from this problem without stating your answers. So what are my intersection points? Where did my line and my parabola cross each other? Okay. -3, 0 and -2, 1. And again, that's why when I'm graphing and I know I'm going to be looking for intersection points, I like to be as precise with my dots as possible. And by rising over running and getting those dots, I didn't just draw a line and think, oh yeah, I think it intersects there. No, I got very specific. I looked for those dots. Okay, guys, that's the idea behind the graph. Okay, now, got a late start today, so hopefully I don't run out of time here. Honestly, what I really want to focus on is the algebra behind this, okay? How do we use the idea of, officially we could say substitution or elimination. Now, because it's a quadratic and a linear, it's going to be easier. Well, I guess I've seen elimination some. I tend to think substitution. What should I do here? Yeah, I was doing substitution. You could do elimination. It could work now that I think about it. But this book teaches us substitution. So let's look at example 2. Solving a linear quadratic system using substitution. So do you remember how substitution works? solve one equation for x equals or y equals. And then once you have it to be x equals or y equals, you take it and put it into the other equation in place of x or y. Now, what do you notice about both of these equations? They're both equal to y. So if they're both equal to y, what's that mean about these two equations? They're equal to each other. They both equal y, they both equal the same thing, so they equal to each other. So the idea, since they're both already y equals, is we're just going to set them equal to each other. It doesn't really matter, which way you do this. I guess I'm going to say that I'm going to take x squared minus 3x minus 20, and I'm going to put it in place here of y, because it's y equals. So let's do this. X squared minus 3x minus 20 is going to equal negative x minus 5. Because both equations were y equals, I could set them equal to each other. Okay. This brings this whole chapter together, folks. How can we solve an equation like this? Combine like terms, and I was trying to make this equation equal to, not equal to x squared, equal to, no? Equal to 0, right? When we're going to have an x squared term, x terms, and number terms, I won't say always, but usually our solving techniques mean we want it equal to 0. So if I want it equal to 0, what do I need to move? I would move the negative x and minus 5. I would keep the positive x squared where it is. So how do you move a negative x? You add x. If I add x on the right, I'm going to add x on the left to my other x term. How do I move a minus 5? You add 5. If you add 5 on the left, we add 5 on the right. So, clean this up, putting like terms together. X squared, what's minus 3x plus x? Minus 2x. Minus 20 plus 5? Minus 15 equals 0. Okay, guys, dig in that chapter 4 brain of yours. I've got a quadratic equation equal to 0. What solving options do I have here? Yeah, I think you're heading in the right direction. Can we factor this? Yeah. When you guys are talking product and sum, multiply and add, we're asking, can we factor this? If this doesn't factor, we have to go quadratic formula. But guess what? It factors. Okay? So, well then, Jaden, you go ahead and use the quadratic formula there. You will come up with the same answers as us. Okay?
But it works for everything.
It does. It's universal. It works. But I like factoring in this case. So, the PS thing, product sum, we're trying to factor this. We need a product of what? Negative 15. And that's because in front of x squared, there's only a 1, right? So we don't have to worry about that. A sum of negative 2. So I need a pair of numbers that multiply to be negative 15 and add to be negative 2. Some combination of 5 and 3, yes, because 5 times 3 is 15. 5 minus 3 is 2. Since we need it to be negative 2, we're going to say negative 5 plus 3. What do I do with that negative 5 and 3? Are those my answers? Goes in the parentheses. X squared is x times x. One parenthesis is x minus 5. The other is x plus 3. I'm not done. Take each factor and set it equal to 0. So x minus 5 equals 0. X plus 3 equals 0. How do we get x by itself? the first equation, you add 5. On the second equation, subtract 3. So I'm going to get x equals 5 and x equals negative 3.
Is that a coincidence that it ended up being the same? I'm just kidding.
The same as what? These?
Negative 5 and 3 say it's not positive.
It's it'll end up being the opposite signs of your factors. And if you're just doing product and sum, now if it's product of AC, that's a different story. But if you're just doing product and sum, it'll end up being the opposite. Now, okay guys, am I done? I didn't box it yet. That is a solid clue.
You have to plug it in.
We have to plug it in. Okay guys, in a substitution, elimination, what kind of answers do we have? We don't just have single answers, we have ordered pairs. Look at the graph up above. What was my answer? It wasn't just 2 numbers, it was 2 ordered pairs. So what I know at this exact moment is that one of my answers is 5 comma something, and my other answer is negative 3 comma something. How do I find my somethings? Plug in those x values where? One of your original equations. So go back to your y equals equations. Which original equation looks easier to you guys? I so agree that I would use the y equals negative x minus 5. Officially, could you use the quadratic? Yes, you can. So, when I put in the 5, it's going to be negative 5 minus 5. And negative 5 minus 5 is negative 10. So one of my answers is 5, negative 10. We also need to plug in negative 3. What's negative of negative 3? 3. And 3 minus 5 is? Negative 2. So my other solution is negative 3, negative 2. And now notice that I did box my answers. There's your ultimate clue that I'm done. Now, could you have used the quadratic and gotten 5 and negative 3? Yes. Okay? And that's a comfort level thing. Okay? I'm going to factor if I can. At least when it's easy factoring. There is something to be said there. Okay. Let's try the other one real quick. Let's practice it. Okay? Yes?
Like on the test, if we were supposed to factor or something, but we did quadratic formula instead, would there ever be something like that?
So in a situation like a problem like this, where it's within part of a problem, I don't care whether you factor a quadratic formula. If it's a section of the test where the directions specifically say solve by factoring or solve using quadratic formula because that's what I'm testing there, then you would need to use what's asked of you. Huh? You won't get full credit. Yes. You would get partial credit for knowing a way to solve, but not knowing the way I asked you to solve, I would only give partial. Okay. Have you guys started the next example? Y equals negative x squared plus 2x plus 10 and y equals x plus 4. What's my plan? Yeah, both equations equal y, so we're basically going to set them equal to each other. Negative x squared plus 2x plus 10 equaling to x plus 4. Okay? What's my next plan here? Okay? Whether I'm going to factor, whether I'm going to have to use quadratic formula, we're going to set equal to 0. So I'm guessing you guys are moving your x and 4. To move a positive x, I'm going to subtract x. I'll subtract it from the other like term. To move the positive 4, we're going to subtract 4. So now I end up with the equation negative x squared plus 1x plus 6 equals 0. Now, if Jaden's using his quadratic formula, he can get started right now. Okay? If we're factoring, what should I probably do before I actually factor? Or what do I encourage you to do? Yeah. I would prefer not to have a negative x squared when factoring. I'm not saying it's impossible, but I would prefer not to. So to get rid of a negative in an equation, multiply by a negative. Now, you can only do that in an equation. You can't just do it to an expression. Okay, but in an equation when it's equals on both sides, you can. So now my equation becomes x squared minus x minus 6 equals 0. What do you think? Does it look like it factors? It does. 2 parentheses. X squared breaks into x and x. We need numbers that do what for us? Okay, multiply to be negative 6. And have a sum or add to be negative 1. You can't see what I'm wrote because I'm off the screen. There we go. Okay, guys. What multiplies to be negative 6 and adds to be negative 1? Yeah. It's a combination of 2, 3, because that's what's going to subtract to be 1, right? Because it multiplies to be negative, we need opposite signs. Because it adds to be negative, larger number negative. So, positive 2, negative 3, is that what you guys settled on back there? Now, are those answers? No, those are factors that go in your parentheses. And I ask that because it's so easy. So many people just stop right there and say, okay, 2 and negative 3 are my x's. No, it's just the opposite, isn't it? Okay. Set each part equal to 0. And when I do that, what x values do I get? Negative 2 and 3. Am I done? No. I want to know where these two graphs intersect, so I need ordered pairs. What do I know about my answers? Yeah, I know the x's. I know negative 2 something and 3 something. How do I find those somethings? In other words, how do I find my y's? Plug them back into one of the original equations. I don't know about you guys, but y equal x plus 4 okay with you guys? Okay. Didn't think you'd mind me picking that one. So, and I get it. Some of you guys may not even be writing the work down at this point. It's pretty obvious. X plus 4, so negative 2 plus 4 is 2. So one answer is negative 2, 2. The other one, plug in 3. 3 plus 4 gives me 7. So ordered pair of 3, 7. Okay, guys. Everyone understand the plan? Lesson 4.9 homework will be due tomorrow like normal. Okay, it is in Math Excel. It is